In this example problem, we have a dog who is located a distance d from the shore, and he's in a boat. And it asks us if the dog is 4.2 kilograms and he's on a 15 kilogram flatboat at a distance 6.1 meters from shore. If the dog then walks 2.6 meters along the boat toward the shore and then stops, and assuming no friction between the boat and the water, how far is the dog then from the shore? Now, the 2.6 meters in the boat is not the actual distance toward the shore, because the boat is going to recoil in the opposite direction in order to maintain the center mass's location. The center mass cannot move here because there is basically no external force applied by the water other than the normal force up. So we're neglecting any type of water friction. And the weight down, so they cancel. So the net force is 0, so the center mass must stay the same location. So let's let the dog move across. Now, you could have started by figuring out a place right here, say, and do your calculations, or you could calculate from where the center mass is located to do its calculation. I'll just do it one way. We'll do it based on the way they've got it, where this is 0. This distance is some distance d. I'm going to put the dog at the back of the boat. The center of the boat, I'm going to say, is right here, and it's at a distance of d minus L over 2, where L is the length of the boat. It doesn't essential that you have to do it this way, but we need to put, somehow we're going to have to be able to tell where the center of the boat is, so it can calculate where the center of mass of the system is. In the beginning, calculating with this being an x equals 0, the center of mass is going to be equal to, and I've got the mass of the dog, times the distance, which is big D, and then plus the mass of the boat, and that's located here at d minus L over 2. So if we put all that together, we have mass of dog plus mass of boat times d minus mass of boat times L over 2. And all of this needs to be divided by the total mass, m dog plus mass of boat. Mass of dog plus mass of boat. Now, this location of the center mass will not change in the problem because there's no net external force. And in fact, I really don't need to care about the bottom here, the denominator, when I actually equate the center masses from both before and after pictures, because the mass of the system will not change in the problem. What I need to do now is to draw a new picture. So the boat's going to move. Let's say it's right here, and the boat moves over like this, and it moves some distance d. So it's not here anymore. It's moved a distance x. The dog, which is now initial location, would have been d plus x, because the whole boat moved over, moves this direction some amount, which it says is 2.6 meters, but which I'm going to represent by just a distance little d. So that means that the distance of the dog is now a new distance, and that distance is d plus x minus little d. And I'm going to recompute the location and equate it to the initial location of the center mass. So like I said, I don't need to really care about the denominators, they cancel out. What I have for the numerator is, initially we had mass of dog plus mass of boat, all of that times d, minus mass of boat times L over 2, and that has to equal my new set of positions, which is the mass of the boat is now at a distance, mass of boat, which was at the distance d minus L over 2, but has now moved a distance x away from that position, plus the mass of the dog, and the mass of the dog is now at a location of d plus x minus little d. D plus x minus little d. And again, both of these could be divided by md. I'll go ahead and do it. By md plus mb. But since both before and after have the same denominator, that denominator is going to cancel out. So that's x center mass. Before picture and after picture. Now let's see if we can't simplify some things. Obviously we can multiply both sides by md plus mb and cancel out the denominators. Over here I want to factor these terms out and see what I get. So let me write the left hand side first. I'm going to leave it alone. Over here I have an MBD and I have an NDD. So that would be MB plus MD, the dog, times big D. I have a minus MBL over 2. I have an MBX. And I have an MDX, so MB plus MD X. And then I have minus MD times D. And looking at this, we can see that this term cancels that term. The boat's length cancels out. And so I have 0 is equal to the mass of the boat plus the mass of the dog times the distance the boat moved minus the mass of the dog times the distance the dog walked. Bringing this over, I now have x is equal to mass of the dog times the distance the dog moved divided by the mass of the boat plus the mass of the dog. Now that's the distance that the boat moved. It's not the question that was asked. The question that was asked was to find the new location of the dog from the shore, which is the distance to d plus x minus this d. In other words, it's this distance right here that I'm asked to find. And I needed to find x because I knew the distance the dog walked and I knew the total distance. So let's put that into that equation. We'll call that x of the dog. So that's d plus x minus d, which is d minus d plus the mass of the dog times d over the mass of the boat plus the mass of the dog. Now because this d is common, I'm going to combine those terms. That's d, and then I get plus, when you multiply mass of the boat times the mass of the dog times dog, you get two terms. You get minus mdd minus mass of boat times d plus mass of dog times d. All of this over mass of the boat plus mass of the dog. And again, we see some things cancel. This cancels the mass of the dog here. And so we get that the distance of the dog, I don't know what a dog is equal to d minus the mass of the boat over the total mass times the distance the dog walked. Now let's see if that makes sense. If the boat was had no mass, then when the dog tried to move, then the boat would take no momentum if it moved in the other direction, and the dog would make no success trying to move in any way. In other words, this term would go to zero, and he would stay the same distance he's always been from the shore. Only the boat would move because it's so much lighter. If the boat was infinitely heavy, then the dog would be able to walk without the boat hardly moving at all. So if the mass of the boat is much bigger than the mass of the dog, you can ignore this term, and this just becomes 1, and it's dog minus the distance the dog walked. So this makes total sense. If you don't get that, you need to do some thinking about it to check the formula, see if it makes sense to you. Now we just put some numbers in. I got distance 6.1 meters. I subtract the mass of the boat. The boat was 15 kilograms over 4.2. So 15 kilograms over 19.2 kilograms. And then we need the distance the dog walks. The distance the dog walks was 2.6 meters. So the distance to the shore, we'll need a calculator to punch this problem up. Pull out our calculator. (15 divided by 19.2 times 2.6 times minus 1 plus 6.1, and we get 4.07 meters. Had you not accounted for the fact that the boat would move and recoil to conserve linear momentum, you would have thought it was 6.1 minus 2.6. You would have thought it'd be 3.5. He's actually further away, and that's because the boat moved away from the shore at the same time he was trying to walk toward the shore. Now, we had something similar to this when I was in college. We had some boats on a pond, and if you and your girlfriend or boyfriend were out there, if you switch sides, if you don't weigh the same, then the boat will shift. And we had things marked in the water, and you could actually see that shift. And from that shift, you could determine, if you knew your own mass, and you knew the mass of the boat, which we did, then you could determine the mass of your boyfriend or girlfriend. So it's a way of measuring your girlfriend or boyfriend without them actually knowing it, if you know the laws of physics. All right, that finishes this example of applying the center of mass to a problem where an object is trying to conserve linear momentum because there's no net external force.